I'll try to be quick. Thank you for the welcome. You see the co-workers for me. Maybe you know Alexander Barth, who is developing actively the NC dataset software. Maybe some of you use it. Now, DIVAnd, what is it about? Well, I'm working in ocean science, so we are, of course, using ocean data. Maybe you have seen satellite data like for the Gulf Stream there. This is nice pictures, but it's only limited to the surface. And you are interested in swimming inside the ocean, so in the deep ocean. There we have Argo floats like in the lower left images. But of course, these data are sparse in time and space, and we have to do something about interpolation. Now, there are a lot of interpolation methods, pure interpolation, polynomial, Chebyshev, and so on, which are strictly passing through the observation point. You have smoothing interpolations, of course, and this is more interesting for us because we have a lot of observing errors on our data. And then you have even more advanced methods where you can try to get the best estimate of your ocean system, assuming you know the errors on the observation and your forecast field, which is called an optimal interpolation, Kalman filter, or Kriging, depending on the domain. Now, so there's a lot of existing software, but we decided to make our own a long time ago because we have two major problems. One is that you have some specific errors on the ocean observations. Typically, errors are correlated. Most of the software don't deal with this. And we have complex geometries. And so Pierre Brasseur in the 90s developed a method where you actually minimize the data analysis misfit, so you want to be close to the data, but you also want to be smooth. So we have a smoothness operator you want to minimize. Don't look at the details. The important point is that you can define this on an actual domain, which has a topology. So you can define boundaries and so on. And when you solve it, the solution automatically takes into account boundary effects. And for example, if you say you have a cruise here with a land part here, if you do a classical interpolation, you propagate the information across the land. And if you use this minimization on the real domain, well, you separate basically both sides of the ocean and you don't have artificial propagation. Now, you can demonstrate that this mathematical formulation is actually equivalent to optimal interpolation if what you call in optimal interpolation your forecast error field is the same as the discrete operator you get from the finite differencing of your first operator you have here. So you have an equivalence between the two, but there's a big difference in terms of practice. In Kalman filter and optimal interpolation, you explicitly define how your covariance function looks like. You decide what it is. In DIVA, it's the operator which defines the derivatives, which creates it for you. So you can control it to some extent, but you have not so much freedom as in optimal interpolation, but you have some similarities. And with this, you can provide, like here, analysis of chlorophyll in European seas, and it has been done for quite some years. And when we started it in '95, it was done in Fortran, very simple finite element code, driven by files and so on. So it went on a shelf because, well, it was difficult to maintain, but still, we were involved in quite some EU projects where we needed to make data interpolation, and it was revived and used in several projects. We added some features, and particularly it was coupled to Ocean Data View, which is a software to manipulate ocean data, which is very often used, and it was put inside ODV as an interpolation software. And Rainer Schlitzer, the main developer, always shows this image. His old interpolation method, again, propagated information from the Pacific to the Atlantic, and with our new software, you just keep them separated naturally. And then, of course, came Julia and Jupiter, and we were asked a lot of times, can you make it more advanced and more dimensional, because this was 2D. And then, of course, Julia with n dimensions was the moment to try to make it more general. We used orthogonal curvilinear coordinates, periodicity, and of course, with Jupyter Notebooks, it's a nice way to ensure documentation and reproducibility for different people. And if you're interested, of course, you can download it here. One important thing, we added a general constraint to the thing. So you can add a quadratic constraint, you can define yourself, and it allows you, for example, to add some additional information, like you know that your interpolated field should obey a tracer advection diffusion equation. You can ensure, for example, that the temperature or concentration of a pollution should remain positive after interpolation, which a lot of interpolation methods don't do. So you can do this by adding this kind of terms, which is nonlinear then, and you have to iterate, but basically you are free to add things like this. An additional feature you can include, once you have error on the forecast field matrices, you can also calculate the analysis error. So you make an interpolation, you get also an interpolation error. It's typically the first example with a barrier. The blue means low error. Basically, it's where you have data, and red, where you don't have data, you have higher error. And we extended now this tool also not only to interpolate, but also to make kernel density estimates. So just points sampled in space, trying to detect where you have high concentrations. A typical example here is, imagine you have an eddy in the ocean where a ship goes across and sometimes make an oil spill. The dots on top would then result. If you have a lot of observation, you can do a classical kernel density estimate. You would have the lower left. And with our approach where you can include some physics, in this case, you would say, okay, I have a current present there, which propagates some information. You would get the right-hand side, which looks very similar, of course. But if you use much less data, only 100 points, you see that classical kernel density estimate just doesn't see the feature, while the other one keeps it. And so we added quite some features. And why were we able to do it? That's why maybe you are interested in this. So one of the major advantages of Julia for us is it reduces drastically development and prototyping. It's 1 or 2 orders of magnitude faster now. When someone asks us a new feature to add it, it's almost immediate. Of course, n dimensions was a major driving force to start with. And we see that now when we share the notebooks with non-experts in Julia, they still can manage to work with it and are quite happy with it. Some of the things we still would like to see different. Well, I'm not the only one. We all are waiting for some static compiler to be able to make a library so people can connect it again to their software. We had some troubles deciding which kind of plotting software to use, because we work on different platforms, and so we moved from PyPlot to PythonPlot to JuliaPlot and now Makey. And personally, I always fall into the trap. I develop in Jupyter, and then when I have to send it to a bigger computer, I just export the Julia script, and then it crashes because I used a local variable somewhere, and I have to reprogram. So I showed it here for ocean science, but actually the core is totally physics agnostic, so it can be used in other domain. It has been used in astrophysics already. So if you're interested in, please contact us, and we can even add some features on demand. That's what we like to do, and well, that's all.
Thank you. Okay, maybe one quick question before the group picture. Okay, maybe I have one question. So you said it was used in astrophysics, and I'm interested because I'm an astrophysics PhD student.
Mm-hmm.
So do you know in which field of astrophysics it was used?
It was used to make density plots, again, kernel density plots, but in a more specific situation.
Okay, maybe I guess galaxies, I don't know. Okay. And actually, the Julia static compiler Julia C was released, I think, a few days ago. I just saw this. So something is changing.
Yeah,